We are going to present the different mechanical methods that can be used for the elaboration of nanomaterials. There are three main methods, and in this first video we are going to concentrate in high pressure and high temperature methods that can be classified in large volume from millimeter to cubic centimeters, or reduced volumes. We can also admit other classifications like static methods or dynamic methods that we will also briefly discuss. So in this first part we are going to concentrate in large volume methods for high pressure and high temperature generation. High pressure and high temperature has been used for many years for the transformation of materials. Graphite transforms into diamond, and this first order phase transformation, it is one of the most used commercially. The diatomic equivalent of graphite, which is boron nitride, also transforms to a cubic structure that is cubic boron nitride. Also very technologically interesting materials. We will discuss about them. They have the characteristic both of being the hardest materials that we know. We start by introducing the difference between static high pressure and high temperature generation and dynamic. So here you have examples of large volume presses that can be used for static generation. So that means that the sample can remain in these thermodynamic conditions in principle for a very long time, hours, days, even weeks. So let's consider now the dynamic generation of high pressure and high temperature. This is done through shock waves. There are two main ways of producing shock waves. One is using guns, multiple stage gas guns, in which the gas is going to be accelerated in large tubes, and in the sample chamber this gas is going to arrive and generate a very high shock pressure on the sample. The other way that is currently used is laser shocks. So the laser is going to be focused, for instance, on a surface in which a plasma is going to be generated, and the explosion of the plasma is going to generate the shock waves. So in all the cases these experiments are very short, and the duration is typically 1 to 2 nanoseconds, and this is the time that you have to make a measurement. So in general, this type of research is used either in academic or military research, and the most fantastic way is result is that the maximum pressure you can reach using laser shocks is about the center of supergiant planets as Jupiter. So it's about 100 terapascal. So let's see different types of large volume, static, high pressure, high temperature devices. One of the most used devices is the piston cylinder one. The maximum pressure that can be reached is about 5 gigapascal, and the principle is very simple. There is a piston here that is going to be pushed by this rod and inserted in a press, and you have then the body of the cell, which is the cylinder cell. So it's a cylinder geometry, and then it can be more or less complicated depending of what you are going to put in the sample chamber. You can have here a manganese resistive device just to measure the pressure, but you can have also heating facilities or windows for optical measurements. The second device that I present here is the belt apparatus. The maximum pressure is about 10 gigapascal, and it is an axial press too, so the force is applied actually on two anvils, and there is a die, what is called the belt, which is going to avoid that the sample that is placed here in a capsule can go out. So there is some extrusion that is going to take place in this region here in the channels, and this was the first device that was used for the man-made diamonds. Multi-anvil cells can reach much higher pressure at the expenses of course reducing volume, and you see that depending on the geometries you can have Walker types of diode type cells. You have here 8 4 in top and 4 in bottom anvils, or here you will have 6 anvils. So the sample that is in the center of the anvils have also some extruding chamber and can also include a heating furnace, for instance. Toroidal anvils are also another kind of axial anvils in which the sample has a window accessible from the sides. So this is a toroidal chamber, and here again you can have also heating devices made of with resistive graphite, for instance. So in this slide you can see some implementations of piston cylinder. Here is in top. Here you find portable type piston cylinder press. Here is a larger one with implemented with a larger press. This one is a belt apparatus. So the belt here is in this part, and you can see here an enlargement of this. So there is this plateau has the top anvil, this plateau has the bottom anvil, and this one has the belt that is encircling the sample. Here you can see examples of multi-anvil presses with a very large press in that side. There is another type here that is going to be implemented in the synchrotron, and you see here examples of the sample chamber in the case of a dia cell or Walker here. Toroidal anvils. These toroidal anvils has been implemented in what is called the Paris-Hindenburg portable cell, and you can see here two examples that are sitting in a X-ray beamline at the European Synchrotron Radiation Facility. So these presses can weight 30 to 50 kilograms, and so it can be really transported from the lab to the synchrotron facilities. So with these devices have been developed industrial synthesis at high pressure of high temperature, for instance of diamond, and these are examples of crystals of diamond obtained at pressure of 5-6 gigapascal and 1500 degrees. So for doing these large crystals you need days to weeks. So most of the industries that are here, what to do is producing powders that are used as abrasive. Synthetic diamond or cubic boron nitride, as shown here, can be produced and of course from the powders, and this is also sold by many companies. High pressure synthesis of diamond constitutes the large diamonds a very small part of the market. That is 2%. So 98% of the diamonds produced at high pressures, high temperatures by men are for abrasive applications. Here you have an example of a synthetic diamond that you can buy on the web, and well, this could seem to you a high price, but in fact for such dimensions, this is 1.6 carats, is not so expensive. Natural one will be more expensive. But can we use high pressure, high temperature to produce real new nanomaterials? And the answer is yes. And here you have an example of nanodiamond produced thanks to the transformation at high pressures and high temperature of nano onions that are concentric fullerenes. And you see here that the size of a polycrystallite obtained that is transparent and is made of nanocrystals of diamond. And the remarkable thing is that this material is harder than diamond. You see, for single crystal diamond, the Knop hardness is 60 to 120 gigapascal. For nanocrystalline diamond, this hardness is up to 140 gigapascal. So here you have an example of a nanodiamond sphere produced in such a way This is a press used for such type of synthesis, and here are commercial rods produce it through high pressure, high temperature, that can be used for machine applications. And these are nanopowder diamond products also that can are commercially available. Another example of high pressure, high temperature synthesis of nanomaterials is twin cubic boron nitride. It is synthesized at 15 GPa and 1800 degrees C, and you can see, as you can see here, when you do X-ray diffraction on these nanotwinned crystals, you obtain this black curve that is very well ordered, and this is very different from this other curve in which the nano cubic boron nitride has been obtained in a different way. So structurally this nanotwin is better ordered, and when one measures here the hardness here as a function of the applied load, one sees that the indentation that one obtains for the nanotwin boron nitride, that is the black curve, saturates at a value that is much higher than the corresponding one for the other form of cubic boron nitride. So this material is harder, or as hard at least as diamond, and the interest is that cubic boron nitride is much more stable than diamond at higher temperatures. So this means that for tooling applications, this is a very interesting material.